This is the assignment 601.2 kinetic energy problem set, and I'm going to work through the questions starting with number 1. Number 1 says, what is the kinetic energy of a 40 kilogram object going 11.3 meters per second? So we learned an equation in class in our notes for kinetic energy, which says that the kinetic energy, or KE, of an object is equal to 1/2 times its mass times its velocity squared. And so if we want to solve for kinetic energy, they have given us, in this question, the mass, and they have given us the velocity. The mass that they gave us is 40 kilograms. The velocity that they gave us is 11.3. So we're going to square just the velocity. The equation doesn't want us to square everything, just that velocity. And we're going to do that, multiply everything together, and that's going to give us our KE. Okay, so half of 40, of course, is 20. 11.3 squared is 127.69, and we're going to multiply that now times 20, to get our answer of 2,553.8. By the way, you can click this button if it's an option to actually use the calculator on the screen, and you can type it in that way. 0.5 times 40 times 11.3. I don't know where squared is. I'm trying to find it. There you go, squared. I typed an extra thing in there. Anyway, you get the hang of it, but it's the same thing. 2553.8. The units are going to be joules for energy. All right, question 2 says, pretend the circles on the diagram below are 3 different balls where their size directly correlates to their mass. Right now I can only see 2 of them, but it's telling us basically that because this is bigger, it has more mass. It's telling us to make that assumption that the bigger one has more mass. Let's see if there's the third one. Okay, so it says if all 3 of these masses are rolling along the ground with the same velocity, rank them from lowest to greatest kinetic energy. So if they have the same velocity, again, kinetic energy is 1/2 mass times velocity squared. But if their velocities are equal, then it's really just their masses that are going to determine the amount of kinetic energy that each has. And the larger this mass is, again, looking at this mathematically, once this thing decides to focus, the larger the amount of mass that they have, the larger the kinetic energy will be. It is a directly proportional relationship, and therefore, because ball 2 is the largest one, it will have the greatest kinetic energy. The next largest is ball 1, so it's got the medium amount, and of course the smallest one, ball 3 in mine, would have the lowest kinetic energy. Again, these are randomized, so yours may have different sizes than mine do. Make sure that you look at the what you have in front of you. All right, this next one says, if an object has a mass of 42.3 kilograms and a kinetic energy of 61,240 joules, then how fast is it going? It's still the same equation, KE equals 1/2 mv squared, but this time we're going to have to substitute in and rearrange a little bit. The kinetic energy in this question is 61,240. We're going to set that equal to 1/2 times the mass, 42.3, times v squared. And so we just need to isolate v squared, but let's go ahead and get half of 42.3 first. And that's going to give us this, 21.15 v squared, and it's still equal to 61,240. Again, if I want to get v by itself, I need to start by getting this 21.15 moved out of here. So I'm dividing both sides by 21.15. That's going to isolate v squared. So let's go ahead and divide that on my calculator, 61,240 divided by that answer, 21.15. Okay, and it gives me this. But again, this is equal to v squared. We need v. So we need to take the square root of this. and that should be our velocity, 53.81, and my units here will be meters per second. Again, when you are working with joules, your masses need to be in kilograms, your velocities need to be in meters per second. That's how everything's going to end up canceling out. If you change the mass of a moving object to become 10 times its original amount, but the velocity remains the same, then the kinetic energy will become blank. It's, again, asking us for the relationship. Okay, so looking just at this equation, not the math that we just did, just at this formula. If you change this so that it is 10 times as much, how does it affect this? And again, you can plug in fake numbers and see what it does. Okay, but this number, if it gets bigger, this gets bigger. And it does so with a directly proportional relationship. This one's not being squared. This one is, that's squared. This is not. Okay, and so if this is 10 times bigger, you're going to get 10 times the energy over there. But again, if you're not sure, plug in some fake numbers and look and see what the factor is that it changes by. But I can tell you right now, mass and kinetic energy have a directly proportional relationship. Question 5 says, an object has 300 joules of energy when it is traveling at 5 meters per second. What is its kinetic energy when it is traveling at 10 meters per second? And so, again, this is really kind of a proportional reasoning thing. And you don't have to do the math to get this, but you can. Okay, if you want to do the math to figure this out, I'm going to show you that way first. Okay, so I know that this object has, again, this is my equation, kinetic energy is 1/2 mv squared, and I know the kinetic energy is 300 initially. I don't know the object's mass, but I do know its velocity initially is 5 meters per second. So when it's traveling at this speed, it has this much energy. So I can figure out the mass of the object, and if I know its mass, I can then solve for its kinetic energy after its velocity doubles. Okay, so let's go ahead and do that. So if I want to do this, let's go ahead and do 300 equals 1/2 m times 25. We're going to move this half over here, so we're going to multiply both sides by 2. That's going to be 600 equals 25m. And then we're going to divide both sides by 25 to get our mass. 600 divided by 25 is going to be, 600 divided by 25 is going to be 24. And so our mass is 24 kilograms. Now that we know the mass and it's the same object, we can go ahead and figure out what its kinetic energy would be when it's traveling 10 meters per second. So what is its kinetic energy now? It's the same object, so it still has a mass of 24, but now it's traveling 10 meters per second. Okay, so find the mass, use it here. Half of 24, of course, is 12. 10 squared is 100. Okay, so KE equals 12 times 100. Okay, and again, you should be able to do this one in your head, but you can type it in the calculator if you need to. 12 times 100, of course, is 1,200 joules. Okay, so what is its kinetic energy now? 1,200 joules. Now, did I have to do all of that? No, I didn't. Okay, because all I had to do was understand what the relationship between the velocity and the kinetic energy of an object is. Okay, because what I basically did in this question is I said, hey, it's initially 5, let's double it. Okay, let's double it to 10. And you should be able to answer what happens to KE when you double velocity. If this gets doubled, just the velocity, if the velocity gets doubled, it doesn't double the KE because that velocity is squared. So if you multiply that number by 2, if you double it from 5 to 10, or from whatever to whatever, if you double something from 2 to 4, whatever, if you double it, you're not doubling this. It's going to change by a factor of 2 squared. Same thing, if you triple it, not what I'm asking, but if you triple it, it would change by a factor of 3 squared. It would be 9 times as much. But in this case, we're doing 2. Okay, so doubling it, it's 4 times as much kinetic energy. Well, the initial kinetic energy was 300. 300 times 4, 1,200. It's a lot faster. You don't have to do all this. You can, but you don't have to if you understand the relationship. So if you double the velocity, you have 4 times the kinetic energy. If your initial kinetic energy is 300, 4 times that, 1,200, or find the mass and then solve for it. Either way, same answer. Question number 6 on 601.2 says, Tommy Jones plays Little League Baseball. He throws a pitch with a velocity that is 1/4 the velocity of Major League pitcher Clayton Kershaw. If Timmy's ball has 1/4 the velocity, how does the kinetic energy compare? So this time I actually don't have enough information to solve it another way. I have to use that proportional reasoning that we just talked about. So again, the equation for kinetic energy is 1/2 mv squared. And in this question, it's saying, hey, what happens if I have 1/4 the velocity? What happens to my kinetic energy? Again, just like in the last question, when I doubled it, it wasn't twice, it was 2 squared. Well, now if it's 1/4, it's not 1/4 as much KE, it's 1/4 squared. Okay, and of course, 1/4 squared is, and you could type this as a fraction, is 1/16. You could type it as a decimal, but it's a lot easier, in my opinion, to do it as a fraction. Up to you, though. But again, you need to understand that this has a squared relationship. So changing this by a factor of 1/4 changes this by a factor of 1/4 squared because the velocity is squared in there. Number 7. Mr. Shell pushes a 20.5 kilogram desk across a frictionless surface for a distance of 3.4 meters. After doing work on the desk, it is moving with positive 191.42 joules of kinetic energy. Find the velocity of the desk. Okay, so how fast is this desk moving? We know, again, the equation for kinetic energy. Write it out again, 1/2 mv squared. So we have this equation. We know how much kinetic energy it has at the end. It's 191.42. And we know the mass of the desk. It's in the question, 20.5 kilograms. We can solve for the velocity of the desk after it has been pushed. Okay, so if I want to do that, I just need to get, let's go ahead and get half of 20.5 and start there. 20.5 divided by 2 is 10.25. And we're going to divide both sides by 10.25. That's going to be equal to v squared. Okay, so 191.42 divided by 10.25. And again, this is not my answer. This is v squared. It's 18.675 equals v squared. And again, that is rounded a little bit. Okay, in order to find just that velocity, we're going to take the square root of both sides. So square root of that number answer in my calculator, and that's what we're going to use. We're going to round this one. Don't round it until the end, 4.32 meters per second. Number 8 says a ball with a mass of 2 kilograms rolls along a track in a physics experiment. If it has an initial velocity of 4.8 meters per second and experiences an impulse of -8 newton seconds, what is its final velocity? So I'm going to start here by labeling some things, and I haven't been doing that super consistently, but it's always a good idea to start by labeling, especially as we add more and more information. So I have a mass, 2 kilograms. I have an initial velocity of 4.8 meters per second. I have an impulse, that's J from the last unit. It's also equal to delta P. Okay, and it's equal to, in this case, a value of -8 newton seconds. What is its final velocity? And then what is its change in kinetic energy? Okay, well, I know a couple of things from the last unit, and that's what this is going to require us to use. Okay, because it's asking for final velocity here. I can't use my KE equation for that. There's only one velocity in that equation. I can find my kinetic energy before this impulse, I can find it after this impulse, but I can't use it to find my final velocity. Okay, and I also don't have the kinetic energy, but what I do know from last unit is that impulse equals not just force times time, but because it's also equal to change in momentum, it also equals mass times change in velocity. And I can use this because remember, change in velocity is VF minus VI. So they gave me the impulse, -8. I can set it equal to the mass, 2, times my change in velocity. And I'm going to go ahead and substitute in VF minus VI. So VF minus VI is 4.8. And we can solve for VF that way. Now you could have solved for delta V and then done this step and found VF, and that's also okay. But if I do it this way, I'm going to go ahead and distribute this in here. So that's going to be 2VF minus 2 times 4.8, which is 9.6, and that's all equal to -8. Again, I need to solve for this, so I need to get this by itself, which the first thing I got to do is move this. Right now it's being subtracted, so we're going to add 9.6 to both sides. That's going to cancel all of that. And 9.6 plus -8, or 9.6 minus 8, is going to give us 1.6 equals 2 times VF. From here, we're going to divide both sides by 2, and that will isolate our variable. So 1.6 divided by 2 is, of course, 0.8, and that would be its final velocity, 0.8 meters per second. What is its change in kinetic energy? Okay, so change in kinetic energy, we can solve for the initial kinetic energy, we can solve for the final kinetic energy, and we can find the change that way. Okay, so the initial velocity is 4.8. The mass was 2. So I can find my KE initial is 1/2 mass times velocity initial squared, and then we'll do the same thing for KE final. Okay, this is going to be 1/2 times 2 times the initial velocity is 4.8 squared. Okay, so half of 2, of course, is 1. So it's really just 4.8 squared, which gives me an initial KE of 23.04 joules. We're going to do the same thing for the final KE. Okay, so KE final is going to be equal to 1/2. The mass is still the same, it's still 2, times the final velocity that we found just a moment ago. Again, it was 0.8. And again, that has to be squared according to the equation, 1/2 mv squared. So again, half of 2 is 1, so it's really just 0.8 squared, which is 0.64. Okay, so here's my initial kinetic energy, here's my final. If I want to find my change in anything, whether it's change in velocity or change in KE, it's going to be our final minus our initial. Okay, so final is 0.64 minus the initial was 23.04, and of course it's going to be a negative change because we lost most of that energy because this object slowed down quite a bit. Okay, but we're going to subtract 0.64 minus 23.04, and that is going to give us our answer, -22.4 joules. Question 9. A 53-gram toy car is pushed from rest with a force of 0.01 newtons for 0.9 seconds. What is its change in kinetic energy? Let's get some fresh paper because we're running out of space on that one. All right, so again, let's start by labeling some things. They have given us a mass of 53 grams. They have given us a force of 0.071 newtons. They have given us a time of 0.9 seconds, and they're asking us for change in KE. Okay, I do know, there's one other thing they gave us, sorry, they gave us an initial velocity of 0 because it says it's pushed from rest. Okay, so that's going to help me out here because what this tells me, if my initial velocity is 0, my initial KE also 0. Okay, so if I want to figure out my change in KE, I really just need to figure out what my final velocity is, because my final velocity will allow me to find my final KE, and of course that will be my change since I started at 0. Okay, so again, label things, see what you have. Looking at this, I can see how I can use some stuff from our last unit, specifically this equation here. F times T equals M times delta V. Okay, again, remember delta V is VF minus VI, and so that's actually how I'm going to substitute it in. But let's go ahead and plug in. F is 0.071, the time is 0.9, it's equal to the mass. Now here's the first thing that we have to take care of before we do anything else. Okay, this mass is in grams. You cannot use grams in these calculations. So before I can substitute this number into my equation, and really I should have stopped to check it here, but before you can substitute it in, you need to convert it to kilograms. There are 1,000 grams in a kilogram, so 53 grams is a really small amount of kilograms. In fact, we have to divide it by 1,000. 53 divided by 1,000 gives us 0.053 kilograms. That's the number I need to use in my calculation. 0.053 times VF, which is what I need to find, minus 0, because that's VI. Now, of course, if I see minus 0, let's go ahead and get rid of that. Okay, so let's go ahead and multiply 0.071 times 0.9. That gives us on this side of our equation 0.0639 equals 0.053 times VF. We're going to divide both sides by 0.053. And when we do that, it gives us a final velocity of 1.206 meters per second. That is rounded, okay? But it doesn't want the final velocity, it wants the change in kinetic energy. So we need to figure out how much kinetic energy this is. We know it started out with 0. So if we figure out how much this is, our final kinetic energy will be equal to our change since we started at 0. Again, kinetic energy is KE equals 1/2 mv squared. We're going to use our final velocity for this one. So our final KE is 1/2 our mass, again 0.053 times our velocity that we just got right here, 1.206 squared. I'm going to square the full value in the calculator. So we're going to do this squared, and then we're going to multiply it by 0.053 and then divide by 2 for the half. And that gives us 0.0385. My unit will be joules because this is energy, and again, this is the final kinetic energy, but because the initial was 0, the change is, if it goes from 0 to this is also the change. So the change in KE will be positive 0.0385, and it does tell us to include at least 3 decimal places. I have 4, which is even better, but make sure you have at least 3. All right, this is the last question, question 10 in the assignment 601.2. It says, a 1,330 kilogram car is initially traveling at 20.9 meters per second. It accelerates at a rate of 0.6 meters per second squared for 3 seconds. What is its final velocity? So again, let's label everything we can. We have a mass, 1330. We have an initial velocity, 20.9. We have an acceleration, 0.6. We have a time, 3. And we're looking for VF. So again, looking at this, I don't see anything I can use from our current unit, but I do see something I can use from unit 2. VF equals VI plus A times T. I'm going to use a kinematic equation. Is there more than one way to do this? Yes. You could do this a different way if you want, but this is how I'm going to go ahead and solve for it. So let's go ahead and plug in. VI is 20.9 plus my acceleration is 0.6. Note, you do need to pay attention to your signs. These are both positive, so I didn't bother writing the positive when I labeled it, but if it were negative, it would be super important for you to label it appropriately. The time here is 3. Okay, so let's go ahead and do 0.6 times 3 plus 20.9, and that gives us a final velocity of 22.7 meters per second. And then it wants to know what is the change in kinetic energy. So again, change in kinetic energy, change in anything is final minus initial. So change in kinetic energy is final kinetic energy minus initial kinetic energy. So we just need to figure out what our final and initial kinetic energies are. We do have a final and initial velocity, and we have a mass, so we can do that. So if I want to solve for my change in kinetic energy, let's go ahead and get our final kinetic energy is going to be 1/2 times 1330 times that final velocity, 22.7 squared, minus initial kinetic energy, 1/2 that 1330 mass times our initial velocity, 20.9 squared. Okay, so I'm just going to do it in one step. Do you have to? No. You're welcome to find this and then find this and then subtract. I was just trying to save a little bit of time. So let's see what we get when we do it this way. It should be the same thing if you do it in steps. All right, so 0.5 times, set it over here so I can see it better, 1330 times 22.7 squared. That's our initial. And then from that, we're going to subtract. I'm going to put some parentheses around this so it keeps it together. 0.5 times 1330 times 20.9 squared. And that should be our change in kinetic energy. 52,189.2, and it should be in units of joules. All right, so again, hopefully that helps you with any questions you have about that, but if you still have questions, please make sure that you ask your teacher during class.